Hi, I'm Elaina Landrum. I'm in Professor Schatz's Physics 2 section, and this is my Lab 2 presentation. This lab relied heavily on the same concepts as Lab 1, including Coulomb's law and conservation of momentum. These two principles allow us to calculate electric forces and fields, as well as to take into account the equilibrium state of balanced forces. Another concept integral to this lab is how electric fields of distributed charges are unique from those of point charges, and what factors determine this. The procedure of this lab was the same as in Lab 1, except now we are treating the piece of tape as though it has a charge that is evenly distributed along its length. My final result is listed below. The lab procedure questions are all data and results taken from Lab 1. The length of 0.152 meters, mass of 0.000152 kilograms, and separation distance of 0.014 meters were measured throughout the experiment, and the gravitational force and electric force were manually computed using these values. The magnitude of the electric force on a piece of tape modeled as a point charge in Lab 1 was calculated to be 1.49 times 10 to the negative 3 newtons, while this magnitude modeled as a distributed charge was calculated to be 2.15 times 10 to the negative 4 newtons. Moving on to the coding section, I used the computational model to find the partial force on each section of the top tape due to the charge of each section of the bottom tape. Using Coulomb's law, along with the net electric force on the top tape, which was yielded by superposition of all the partial forces, I found the charge on one piece of tape to be 1.10 times 10 to the negative 5 coulombs. In terms of assumptions, I ignored air resistance on the moving object, and I stated that each U-tape used in the experiment had the same amount of charge. Further, I assumed that the charge on each U-tape was quite evenly distributed, and that each small piece of each U-tape had the exact same charge. We modeled the tapes as point charges in Lab 1, which involved rearranging Coulomb's law to determine the charge of the tape given the equilibrium force balance. The estimated charge with a computational model using this method was determined to be 5.70 times 10 to the negative 9 coulombs. The charge determined by a distributed charge computational model was 1.10 times 10 to the negative 5 coulombs. These estimates are very different because in the point charge model we are pretending like all the charge is acting directly at the center of the tapes, while in the distributed model we split the charge up into 10 different pieces and have these partial charges acting from the center of the respective partial pieces. The distributed charge model is more likely to be closest to the real value of the charge because objects in real life act more like distributed charges with infinitely small sections and partial charges. In conclusion, this lab really hit home the concepts of Coulomb's law and its importance and relationship to electric charges, force vectors, and field vectors. The computational, visual, and practical differences between the point charge and distributed charge models are much more apparent to me after completing this lab. In conclusion, this lab really hit home the concepts of Coulomb's law and its importance and relationship to electric charges, force vectors, and field vectors. The computational, visual, and practical differences